Understanding Surds, a comprehensive guide to working with irrational numbers in radical form. Lesson Overview. Definition of surds. Understanding what makes a number a surd. Like surds, identifying surds with the same radical. Simplification. Techniques to reduce surds to their simplest form. Addition and subtraction. Combining like surds. Multiplication and division. Operations with surds including rationalization. Definition of surds. A rational number can be expressed as a quotient of m divided by n, where m and n are integers, and n is not equal to 0. An irrational number is any real number that is not rational. Surds are irrational numbers expressed in the form of roots. Examples of irrational numbers: square root of 2, square root of 3, pi, and other roots that cannot be expressed as rational numbers. In square root of m, the symbol square root is called a radical, and m is the number under the radical sign. Like surds. Two or more surds are considered like surds if they have the same number under the square root or other root sign. Example 1. Square root of 3, 2 times square root of 3, and 5 times square root of 3 are like surds because they all have 3 under the radical. Example 2. Cube root of 4, 3 times cube root of 4, and 6 times cube root of 4 are like surds because they all have 4 under the cube root. Non-example. Square root of 2 and square root of 3 are not like surds because they have different numbers under the radical. Like surds can be combined through addition and subtraction. Simplification of surds. To simplify a surd, we look for perfect square factors under the radical sign. Step 1. Express the number under the radical as a product, where one factor is a perfect square. Step 2. Take the square root of the perfect square factor. Step 3. Multiply this result by the square root of the remaining factor. Simplification examples. Example 1. Square root of 45 equals to square root of open bracket 9 times 5 close bracket equals to square root of 9 times square root of 5 equals to 3 times square root of 5. Example 2. Square root of 150 equals to square root of open bracket 25 times 6 close bracket equals to square root of 25 times square root of 6 equals to 5 times square root of 6. Example 3. 3 times square root of 75 equals to 3 times square root of open bracket 25 times 3 close bracket equals to 3 times 5 times square root of 3 equals to 15 times square root of 3. Remember, the goal is to find the largest perfect square factor possible. Expressing as a single surd. Example 1. 5 times square root of 2 equals to square root of open bracket 5 squared times 2 close bracket equals to square root of 50. We have converted a coefficient and a surd into a single surd expression. Example 2. 2 times square root of 11 equals to square root of open bracket 2 squared times 11 close bracket equals to square root of 44. This technique is sometimes useful for certain types of calculations. Converting between forms, coefficient times surd and single surd, can make certain operations easier depending on the context. Addition and subtraction of surds. Only like surds can be directly added or subtracted. Before performing these operations, simplify the surds if possible. Key rule: a times square root of c plus b times square root of c equals to open bracket a plus b close bracket times square root of c, where a and b are coefficients, and c is the number under the radical. Important note: square root of a plus square root of b does not equal to square root of open bracket a plus b close bracket. This is a common mistake. The sum of surds is not equal to the surd of the sum. Addition and subtraction examples. Example 1. Square root of 12 plus square root of 3 equals to square root of open bracket 4 times 3 close bracket plus square root of 3. This is obtained by factoring 12 to find the largest perfect square. Equals to 2 times square root of 3 plus square root of 3. This is obtained because the square root of 4 equals to 2. Equals to open bracket 2 plus 1 close bracket times square root of 3 equals to 3 times square root of 3. This is obtained by combining like surds. Example 2. 2 times square root of 12 minus 3 times square root of 3 plus 4 times square root of 75 equals to 2 times open bracket 2 times square root of 3 close bracket minus 3 times square root of 3 plus 4 times open bracket 5 times square root of 3 close bracket. This is obtained by simplifying each surd to its simplest form. Equals to 4 times square root of 3 minus 3 times square root of 3 plus 20 times square root of 3. This is obtained by multiplying the coefficients with the simplified surds. Equals to open bracket 4 minus 3 plus 20 close bracket times square root of 3 equals to 21 times square root of 3. This is obtained by combining like surds. Always look for opportunities to simplify surds first, then combine like terms. Multiplication of surds. Remember, after multiplying surds, check if the result can be further simplified. Basic rules. Square root of a times square root of b equals to square root of open bracket a times b close bracket. A times square root of c times b times square root of d equals to a times b times square root of open bracket c times d close bracket. First simplify if possible, then multiply whole numbers with whole numbers and surds with surds. Multiplication examples. Example 1. Square root of 27 times square root of 50 equals to square root of open bracket 27 times 50 close bracket. This is obtained as the product of two square roots equals to the square root of the product. Equals to square root of 1350. This is obtained by multiplying 27 and 50. Equals to square root of open bracket 9 times 150 close bracket. This is obtained by finding a perfect square factor in 1350 to simplify the surd. Equals to 3 times square root of 150. This is obtained because the square root of 9 equals to 3. Equals to 3 times 5 times square root of 6 equals to 15 times square root of 6. This is obtained as 150 equals to 25 times 6, and the square root of 25 equals to 5. Example 2. 4 times square root of 3 squared equals to 16 times 3 equals to 48. This is obtained when squaring a term with a surd, the coefficient is squared, and the surd is squared separately. When squaring a surd, the square root of 3 squared equals to 3. Example 3. Square root of 32 times square root of 6 equals to square root of open bracket 32 times 6 close bracket. This is obtained as the product of two square roots equals to the square root of the product. Equals to square root of 192. This is obtained by multiplying 32 and 6. Equals to square root of open bracket 64 times 3 close bracket. This is obtained by finding the largest perfect square factor of 192 to simplify the surd. Equals to 8 times square root of 3. This is obtained as the square root of 64 equals to 8. Multiplying binomial surds. When multiplying expressions with multiple terms containing surds, use the distributive property. Example 1. Open bracket 3 times square root of 5 plus 2 close bracket times open bracket square root of 5 plus 3 close bracket equals to 3 times square root of 5 times square root of 5 plus 3 times square root of 5 times 3 plus 2 times square root of 5 plus 2 times 3. This is obtained by applying the distributive property to multiply each term in the first bracket with each term in the second bracket. Equals to 3 times 5 plus 9 times square root of 5 plus 2 times square root of 5 plus 6. This is obtained because the square root of 5 squared equals to 5, and coefficients are multiplied with surds where appropriate. Equals to 15 plus open bracket 9 plus 2 close bracket times square root of 5 plus 6. This is obtained by combining like surd terms. Equals to 21 plus 11 times square root of 5. This is obtained by adding the constants 15 and 6. Example 2. Open bracket 3 times square root of 7 minus 2 times square root of 3 close bracket times open bracket 5 times square root of 7 minus 2 times square root of 3 close bracket equals to 15 times 7 minus 6 times square root of 21 minus 10 times square root of 21 plus 4 times 3. This is obtained by applying the distributive property and multiplying each term carefully. Equals to 105 minus 16 times square root of 21 plus 12. This is obtained by combining like surd terms and constants. Equals to 117 minus 16 times square root of 21. This is obtained by adding the constants 105 and 12. Special products with surds. Difference of squares. Open bracket a plus b close bracket times open bracket a minus b close bracket equals to a squared minus b squared. This is obtained from the standard difference of squares formula. Example: open bracket 5 times square root of 6 minus 3 close bracket times open bracket 5 times square root of 6 plus 3 close bracket equals to open bracket 5 times square root of 6 close bracket squared minus 3 squared. This is obtained by applying the difference of squares formula, equals to 25 times 6 minus 9. This is obtained by squaring 5 times square root of 6 to get 25 times 6 and squaring 3 to get 9, equals to 150 minus 9 equals to 141. This is obtained by subtracting the constants. Perfect square trinomial. Open bracket a plus b, close bracket squared, equals to a squared plus 2 times a times b plus b squared. This is obtained from the standard perfect square trinomial formula. Example: open bracket 7 times square root of 13 plus square root of 5 close bracket squared equals to open bracket 7 times square root of 13 close bracket squared plus 2 times open bracket 7 times square root of 13 close bracket times square root of 5 plus open bracket square root of 5 close bracket squared. This is obtained by expanding the square of a binomial. Equals to 49 times 13 plus 14 times square root of 65 plus 5. This is obtained by squaring 7 times square root of 13 to get 49 times 13, multiplying 2 times 7 times square root of 13 times square root of 5 to get 14 times square root of 65, and squaring square root of 5 to get 5, equals to 637 plus 14 times square root of 65 plus 5 equals to 642 plus 14 times square root of 65. This is obtained by adding the constants 637 and 5. These patterns can save time and reduce errors when working with complex surd expressions. Division of surds. Rationalization. When a fraction has a surd in the denominator, we typically rationalize it to remove the surd from the denominator. Identify the denominator. Determine if the denominator is a monomial, which has a single term, or a binomial, which has 2 terms. This is obtained to decide the appropriate rationalizing method. Choose rationalizing factor. For square root of b in the denominator, multiply both numerator and denominator by square root of b divided by square root of b. This is obtained to remove the surd from the denominator. For a binomial denominator, open bracket a plus b times square root of c close bracket, multiply both numerator and denominator by open bracket a minus b times square root of c close bracket, divided by open bracket a minus b times square root of c close bracket. This is obtained to convert the denominator into a rational number using the difference of squares. Multiply and simplify. Multiply both numerator and denominator by the chosen rationalizing factor. This is obtained to maintain the equality of the fraction. Simplify the resulting expression. This is obtained by performing all multiplications and combining like terms to produce a simplified fraction without a surd in the denominator. Rationalizing monomial denominators. Example 1. 3 divided by square root of 5 equals to open bracket 3 divided by square root of 5 close bracket times open bracket square root of 5 divided by square root of 5 close bracket. This is obtained to remove the surd from the denominator. Equals to open bracket 3 times square root of 5 close bracket divided by open bracket square root of 5 close bracket squared. This is obtained by multiplying the numerators together and the denominators together. Equals to open bracket 3 times square root of 5 close bracket divided by 5. This is obtained because the square root of 5 squared equals to 5. Equals to open bracket 3 divided by 5 close bracket times square root of 5. This is obtained by separating the coefficient from the surd. We have removed the surd from the denominator. Example 2. 21 divided by square root of 6 equals to open bracket 21 divided by square root of 6 close bracket times open bracket square root of 6 divided by square root of 6 close bracket. This is obtained to remove the surd from the denominator. Equals to open bracket 21 times square root of 6 close bracket divided by open bracket square root of 6 close bracket squared. This is obtained by multiplying the numerators together and the denominators together. Equals to open bracket 21 times square root of 6 close bracket divided by 6. This is obtained because the square root of 6 squared equals to 6. Equals to 7 divided by 2 times square root of 6. This is obtained by simplifying 21 divided by 6. Always check your work by verifying that the denominator no longer contains any surds. Rationalizing binomial denominators. When the denominator contains two terms, called a binomial, we use the conjugate to rationalize. This is obtained to remove the surds from the denominator. Find the conjugate. The conjugate of open bracket a plus b times square root of c close bracket is open bracket a minus b times square root of c close bracket. This is obtained to apply the difference of squares method. For example, the conjugate of open bracket 2 times square root of 2 minus 1 close bracket is open bracket 2 times square root of 2 plus 1 close bracket. This is obtained by changing the sign between the two terms. Multiply by the conjugate. Multiply both numerator and denominator by the conjugate of the denominator. This is obtained to create a rational denominator while keeping the value of the fraction unchanged. Use difference of squares. Open bracket a plus b close bracket times open bracket a minus b close bracket equals to a squared minus b squared. This is obtained to eliminate the surds in the denominator. Applying this formula ensures that the denominator becomes a rational number. Binomial rationalization example. Example: 6 divided by open bracket 2 times square root of 2 minus 1 close bracket. Step 1. The conjugate of open bracket 2 times square root of 2 minus 1 close bracket is open bracket 2 times square root of 2 plus 1 close bracket. This is obtained by changing the sign between the two terms to apply the difference of squares. Step 2. 6 divided by open bracket 2 times square root of 2 minus 1 close bracket equals to open bracket 6 divided by open bracket 2 times square root of 2 minus 1 close bracket times open bracket 2 times square root of 2 plus 1 close bracket divided by open bracket 2 times square root of 2 plus 1 close bracket. This is obtained by multiplying both numerator and denominator by the conjugate to rationalize the denominator. Step 3 equals to open bracket 6 times open bracket 2 times square root of 2 plus 1 close bracket divided by open bracket 2 times square root of 2 minus 1 close bracket times open bracket 2 times square root of 2 plus 1 close bracket. This is obtained by combining the numerators and denominators. Step 4 equals to open bracket 12 times square root of 2 plus 6 close bracket divided by open bracket 2 times square root of 2 close bracket squared minus 1 squared close bracket. This is obtained by applying the difference of squares formula to the denominator. Step 5 equals to open bracket 12 times square root of 2 plus 6 close bracket divided by open bracket 8 minus 1 close bracket equals to open bracket 12 times square root of 2 plus 6 close bracket divided by 7. This is obtained by simplifying the squares in the denominator. Final answer: open bracket 12 times square root of 2 plus 6 close bracket divided by 7. The denominator is now a rational number, 7, with no surds. Evaluating expressions with surds. When evaluating expressions with surds, it is often helpful to rationalize the denominators first. Approximate decimal values. Square root of 2 is approximately 1.414. Square root of 3 is approximately 1.732. Square root of 5 is approximately 2.236. Example: evaluate 2 divided by square root of 3. Step 1. 2 divided by square root of 3 equals to open bracket 2 divided by square root of 3 close bracket times open bracket square root of 3 divided by square root of 3 close bracket. This is obtained to rationalize the denominator. Step 2 equals to 2 times square root of 3 divided by open bracket square root of 3 squared close bracket. This is obtained by multiplying the numerators together and the denominators together. Step 3 equals to 2 times square root of 3 divided by 3. This is obtained because the square root of 3 squared equals to 3. Step 4 equals to 2 times 1.732 divided by 3, approximately equals to 1.155. This is obtained by substituting the approximate decimal value of square root of 3 and performing the calculation. Practical applications of surds. Geometry. The altitude of an equilateral triangle with side 12 cm is given by h equals to open bracket s times square root of 3 close bracket divided by 2. This is obtained from the formula for the altitude of an equilateral triangle. Substituting s equals to 12 gives h equals to open bracket 12 times square root of 3 close bracket divided by 2. This is obtained by multiplying the side length by the square root of 3, equals to 6 times square root of 3 centimeters. This is obtained by dividing 12 times square root of 3 by 2. This exact form is more precise than a decimal approximation. Trigonometry. If tangent of x equals to 1 divided by open bracket 3 times square root of 2 close bracket and 0 degrees less than or equal to x less than or equal to 90 degrees, then cos x minus sin x equals to open bracket 3 times square root of 2 minus 1 close bracket divided by 2. This is obtained by using surds to express exact trigonometric values. Surds allow for exact values in trigonometric calculations. Key takeaways. Simplify first. Always look for opportunities to simplify surds before performing operations. Like terms. Only like surds, same number under the radical, can be directly added or subtracted. Rationalize denominators. When a surd appears in a denominator, rationalize to remove it for cleaner expressions. Exact values. Surds provide exact values rather than decimal approximations, which is valuable in mathematical proofs. Remember, practice is essential for mastering operations with surds.